I'd like to talk to you about technology that empowers human intelligence, or the ability to make decisions to create a better built world that we live in. Every corner on the planet has just one location, a north, an east, and elevation, and it should have a description of what that point is. I'm going to talk to you about the basic elements of drawing the site plans used for approvals. A line is a point that goes from one northeast coordinate to another northeast coordinate. That's called a line entity. A polyline is a line that begins at a coordinate, goes through a series of coordinates, and ends at a coordinate. Curves are drawn various ways. They start at a north and east coordinate, a center location, and then they swing an arc to an end point. Those are the basic elements of a site plan to be submitted in CAD or CDIS, Coordinate Design and Information System. What's GIS? It ties information to a map. The map is entirely drawn by polylines. Why? Because in 1975, when computers had no speed or power, it took forever just to draw a single curve. So instead, they draw a bunch of tiny little points along a polyline that appears like a curve, but it was very fast. So that way you could get a map of a whole county regenerated in a reasonable amount of time. But that was 50 years ago. But that's still why our maps are being built with polylines. A closed polyline is called a shape. So a shape file can be polylines that create buildings in a city, or lot lines in a city. Could be another shape file. And another shape file might have utility lines. So shape files are another way to layer different information. So there are no layers in GIS, essentially, and there could be hundreds of polylines in a single shape file. There are no curves in GIS. Again, tiny little lines along that polyline that appear like a curve, but it's not a curve. And because of that, and also other inaccuracies, GIS should never be used for engineering, surveying, or design applications. So a closed shape can contain area, but the area is likely wrong, especially if there's a curve. And the way it works is when you have two adjacent shapes, you have replication of the lines on top of each other if they're actually the same line, and points on top of each other. So there's a lot of replication of data, but screens can refresh fairly fast. So what's CAD? CAD is a collection of individual lines and curves that when it comes to a common point, has that point replicated because the line that it ends at and the line that it continues from doesn't know that they exist together, whether they're lines or arc entities. So on this drawing, simple drawing of just 6 points, there's 13 coordinates. Like GIS, it replicates data, but CAD is likely to be more accurate. So because these points are not fused together, they're not the same point, in order to define area, one must take a polyline and define that area by pointing to these individual entities and points. So the chance of a human error is actually pretty great, especially when things are very complex. So area is done on a separate layer than all the layers that you already have stacked on top of each other and all the points that are already stacked on top of each other. But land surveying requires us to know what that point is. So when CAD draws an airplane wing or a car fender, who cares what points they are? In surveying, you need to know what those points are. And there's no mechanism in either GIS or CAD to do that within the data structure of the drawing itself. So what happens is they have blocks of data on top of all this other data, and all the calculations are done on the separate data structure that's hooked hopefully into the drawing. So if this starts to sound complex, you better believe it is. And the more information and the more automation that we get in CAD-based systems, the worse it gets. Global positioning, or GPS, is what drives the maps on your car. But because of line of sight, the surveyors are still going out there with their transit and their survey crew to get the exact points on the ground. So as great as it is, it's still not used for land surveying, but it can provide an accurate northeastern elevation. LiDAR, light detection and ranging, again, relating to your car, that pedestrian avoidance system is probably LiDAR technology. From an airplane or a drone on an acre of land, it'll take a point every 2 feet or so, randomly, so it'll consume about 10,000 points per acre. Whereas a land surveyor can define that same topography with maybe somewhere between 20 and 50 points. And because it's random, it's never going to get detail like top of curb, bottom of curb, good definition of ditches, homes. That little hill that you see might be a parked car or thick vegetation. Again, it still doesn't replace the precision and the accuracy of a survey crew, but it's automated. And that brings a large problem with LiDAR. It can produce a map like you see here. That contour line that does this doesn't exist. Contours are nice, smooth lines, not jiggly, spastic lines. The problem is there's a point about every foot along that line. That line probably contains 10,000 wrong points. And it's because someone downloaded the data, hit a button in software, and gave a plan to the county or the city, or in this case, our team. Now, all these mapping software companies have the ability, through extra software or training or what have you, to create an actual, real contour map, not this jiggly stuff. So what we do and what everybody should do when they get a map like this from a LiDAR mapping company is refuse to pay. And it's amazing how fast we get a contour map back that's actually usable. But this is digital garbage, and it overloads the surveying and the engineering firms that'll take this data and actually use it. But because the general public and even a lot of the people in the consulting industry don't even realize this digital garbage, it actually renders the calculations of the critical engineering and surveying unusable. They blindly go ahead and accept this data. And that's the main problem with LiDAR maps. So once we get the correct map with smooth contours, we can take it and put it through a filter. So instead of 50 million points, rendering all the calculations as slow as a snail, we can reduce that 50 million points to about 20,000 points, and everything goes smoother and faster, and it's the exact same surface. So this brings us to the solutions, CDIS. Computer Design and Information System. So before 1982, all surveying and civil software drafted site plans based on a CDS type technology. In other words, a software vendor had to get a drawing out, so they had to create their own drafting package. They were computing one point in memory that contained the northing, easting elevation and a description, and then created the lines and curves from those points. After 1982, software developers abandoned developing their own drafting, and instead they could work on top of AutoCAD. That's all except for one company. That was my company, Land Innovation. Instead, we decided to improve the drafting and develop the first surface-based system, because surfaces are the world we live in, not lines and arcs. And all those companies, there was like 50 of them that went on top of AutoCAD. 95% of them didn't exist after AutoCAD came out with their own civil and surveying package. They competed against all these other competitors that went on their platform. And meanwhile, in the 80s and 90s, Land Innovation did quite well, allowing consultants using that software to far outperform and get better work than the AutoCAD-based competition. So again, the CDIS, the only thing that exists is the points themselves. Land Innovation had a point number, northing, easting, elevation, and a description. Today, we've eliminated the point number because we could track that location on the planet. This significantly makes all the processes less cumbersome and easier. And all we do is we draw the lines and arcs between these points, so that if we have 1,000 lines coming to one point, there's only one point in memory, and we know what that point is. Is it a building corner? Is it a lot corner? And we can track information on what that point is, and not some point number management system. There's only one point that defines the center of a curve. So along a curve, when you have utilities and pavement and centerline and right-of-way, there's only one point in memory. Because these elements are all fused together, all we have to do to define area is point inside a closed area and tell it what that area is, what type of surface that represents. Is it a lot? Is it a driveway? Is it a sidewalk? Is it a living room of a house? Is it a wall or a window? So GIS is spatial, but it's highly unlikely it's ever going to be accurate. CAD can be accurate, but it's not spatial. And Both of these are incredibly inefficient and incredibly complex, versus this, which is incredibly simple. It is the only precision spatial option today for land development industry. But today it adds a lot of intelligence to the spatial data instantly. And it's the foundation for very quick and easy 3D and VR. So let's talk about learning curves. Well, GIS is years, typically in an urban planning course. CAD can be years for surveying, civil engineering. There are thousands of commands, intentionally complex, which drives the support and the training fees. Again, CDIS is incredibly simple. In addition, it's got our patented graphic and video prompts, not just making it easy, but making it fun to use. Our goal was 2 weeks or less for the entire system. We're talking about civil engineering, planning, architecture related to the site, land surveying, precision mapping in a few weeks, without needing any CAD or GIS experience or any special computer skills. And this allows us instead to use the months or years reduced of learning the technology to teach the future surveyors, engineers, architects, and planners how to think differently and do their job better. So there's two major advantages I want to address here. One is the environmental density, which is impervious surface analysis of any new proposal, which provides valuable information for both the designer and the cities that adopt this technology. And with a fraction of the data, we could go into interactive 3D and VR quicker and easier than any other technology. So that future of VR is today. And we were the first on the planet to use VR in public meetings back in 2015, and we're still the leaders in that technology. So let's take a look at Land Mentor in a map in vintage mode. This mode was developed because cities and counties are still using the drafting standards of 100 years ago. We could argue 200 years ago. But each of those crosshatches or stipples represent a different type of surface, whether it's the pool, the street pavement, the sidewalks, the houses, the driveways, or the lots, etc., and so on. Those are surfaces that we live in, surfaces being proposed on a raw site. And with those surfaces, we can run all kinds of analysis. So those are called fills. And we have a fill list. A fill list could be colors or textures, and it's a simple name defined by what type of surface it is. So if it's impervious, it's man-made. It's as simple as that. And you can see we have vintage mode on, so we can press that button to turn it off, and that changes the exact same plan into colors and textures, eliminating the need of something like a Photoshop to embellish a plan. In fact, it eliminates drafting entirely, because in the normal engineering and surveying process, drafting is a byproduct. And think about this. We've designed at least $200 billion worth of land development over the years. We've never had a draftsman in our company. We've never had to embellish a plan with Photoshop because it's surface-based. So let's talk about the green button, which reports all the impervious surfaces. So pressing that, everything that's tagged impervious is drawn in white. And we could see the community building was not drawn in white. So there's a mistake. Then there's a list of the square footages and acreage of every man-made item, which internally is accurate to 1/1,000,000th of a square foot. But numbers tend to confuse people, like city council and planning commissions. The more numbers they see, the more questions they ask. So going back to the fill list, all we had to do was take that park building and tag it impervious, and that fixed the problem. And then we chart the same data. Now with the chart, we go into the planning commission and council, and we say, well, here's all the man-made elements and colors and textures that match the plan. Look at all the green space we're providing. Who cares about the numbers? The most important number is the one on the top, that 33.5% of man-made elements that impact the site. So think about that. On this site plan, it'd take you a month in CAD. Well, this is a sidewalk, this is a driveway, this is, and every one of those would need a polyline on a different layer to get the area, and the chance of human error is phenomenal. Where in a plan like this, it may have taken 2 extra minutes at most. And this is critical data for the designer because the lower that number, the more efficient that plan. So think of it as like the miles per gallon on the car. That window sticker, you want to go to the highest number possible. On the environmental density, you want to go to the lowest number possible. So initially when someone does a concept plan, they can have the initial numbers that are exact to a millionth of a square foot and go, wait a second, that number is pretty high, maybe I should revisit the design. So again, the lower the number, the more efficient the design. So let's talk about 3D. Going into VR and 3D, before we go into VR and 3D, we just activate the fills that we want to drop and overlay on the topography. That's just one button. Everything else is automatic. And what happens is either myself or my son Adam, my right-hand man, starts a job and we start designing. Ricky at our office is building the 3D models of our clients in SketchUp. So by the time we're designing the plan, Ricky has created the SketchUp models back into Land Mentor format, and these two processes converge, and we could set, say, 100 homes at the correct location and the correct elevation automatically in about 15 minutes. Another hour or two, we had people, cars, trees, other embellishing items, and then we are done with the 3D process. So 3D, not some 2D plan that looks like it came out of the 1800s, becomes the normal communication tool. And that 3D is VR ready so that we can put on VR headsets and our world disappears and we're into this new world where you feel the space. And that way cities can make proper judgments on submittals. The designer can experience what they're designing and make changes before the client ever sees it. The client gets delivered this 3D file that they don't need any software to run, and if they have a gaming computer, take an Xbox 360, move about themselves, and if that computer has a VR headset capability, down that headset, and they're in the site. That further can be used after the approvals for marketing. And because it's so quick and easy, because of the CDIS technology, there's no extra charge. So as you can see, the future isn't CAD, and it's not GIS, because currently the industry is building highways with bobcats. We're the bulldozer that's going to redefine the entire land development industry. Thank you for your time.